What theoretical models or simulations can be developed to predict how moisture-induced deactivation occurs in O3 NaCrO2 and to guide further material optimization? How do these challenges with water absorption and surface deactivation in O3 NaCrO2 compare with similar issues in other cathode materials, and what insights can be drawn from those comparisons? What are the most pressing research questions that need to be addressed in order to improve the cycling performance of O3 NaCrO2 and bring it closer to practical application in sodium-ion batteries? Can Davis Syrinz manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the Ni-based O3 9io2 material achieve a monoclinic rhombohedral lattice? And what does this unique lattice arrangement imply for its electrochemical behavior? In what ways is its structure similar to that of alpha-NaFeO2? And what lessons can be drawn from this similarity regarding stability and performance? How does the NiO layer sharing the same edge with each NiO6 octahedral structure contribute to the overall integrity and conductivity of the material? And what impact does this have on ion transport within the electrode? Why is it significant that, in non-IO2 materials, Ni superscript 2 cannot occupy the positions typically reserved for sodium ions? And how does this ionic exclusion affect the charge transfer processes during intercalation and deintercalation? How do these structural features together determine that O3 type non-IO2 exhibits electrochemical properties similar to those of NaCrO2? And what implications does this have for its practical application in sodium-ion batteries? What are the underlying mechanisms by which the monoclinic rhombohedral lattice and edge sharing octahedra facilitate or hinder electron and sodium-ion mobility? And how might this influence the cycling stability and rate performance of the electrode? In what ways could further modifications such as appropriate doping or structural tuning optimize these characteristics to enhance battery performance? How does the similarity between the structures of O3 9io2 and other related materials like NaCrO2 and alpha-NaFeO2 inform our understanding of their ion migration pathways and overall electrochemical behavior? What experimental methods and theoretical models can be used to investigate in greater detail the impact of the specific lattice configuration on the material's conductivity, stability, and capacity retention? How might understanding the role of such structural characteristics guide future research towards developing advanced electrode materials with improved performance and durability for sodium-ion batteries? How does synthesizing 9io2 using Na2O and NeO in an oxygen atmosphere influence the crystal structure and defect formation of the material, and what impact does this have on its overall electrochemical performance? What?